Hello everybody, welcome to another Gregorius Maths video. I'm not even going to lie to you guys, I only just clocked like half an hour ago that it was Sunday. Pretty sure it's Sunday today. Yeah, this theorem of the week today is quite a good one actually, it's quite a spicy one. It's the Hopf invariant 1 problem. And in this video I'm going to be using K-theory to prove it. I know that the original proof by Adams was done with some cohomology operations, but it was later discovered, I think by Adams himself and some others as well, that you can prove it much more easily with K-theory. And so that's the proof that I'm going to be presenting today. So yeah, let's get into it. By the way, I'm going to be defining the Hopf invariant in terms of K-theory, which is not standard at all. The standard definition is in terms of cohomology and stuff like that, but this is an equivalent definition, and I won't go into why it's equivalent because that's not the point. I'm not here to explain in detail the Hopf invariant. I'm more here to just prove the Hopf invariant 1 theorem. So, for our purposes, this is how we're going to be defining the Hopf invariant. So, we start off with a map between the 2n-1 sphere and the n sphere. And using this map, we can use it as an attaching map. So we attach the n sphere via this map F to a 2n cell, so the 2n disk, and we attach it via F. And with this, we can form a cofiber sequence. If you don't know about cofiber sequences, check out my video on fibrations. So we can form this cofiber sequence here, which again, check out my video on cofibrations and fibrations to see that this will induce an exact sequence of this form. And so what do we have here? So we've got this exact sequence, and since this reduced K theory here is the integers, it's projective, so the sequence splits. And so we have that the reduced K theory of X, our space formed by this push out here, is indeed just the sum of the K theory of the 2n sphere plus the reduced K theory of the n sphere. And so if we pick a generator iota n for the reduced K theory of the n sphere, then in fact the following two elements define a basis for our reduced K theory of X. So what's alpha? Alpha is this map pi star, and you apply it to the generator of this K theory group here. And beta is the element such that I star of beta, I should probably say, is it generates this reduced K theory here. And so we see that beta squared, well, I'm just going to say beta, beta squared is equal to some integer times alpha. And that integer is what we will define to be the Hopf invariant. And today's problem is concerned with when can this integer be 1? Turns out that only 3, we'll get into it. We also need, so that's the definition. So the Hopf invariant is the number such that beta squared is equal to h of f times alpha. Okay. Now, we also need to use the Adams operations. And again, I won't go into much detail about what they are. If you want prerequisites about K-theory, actually, then I have an old talk that I did about K-theory. I'll try and remember to link these in the description or something. But anyway, okay, let me proceed. The Adams operations are family of maps, psi k, which go from the K theory of X to the K theory of X. They satisfy the following. So firstly, from properties 1 and 3, they are a ring homomorphism. Secondly, if X is a line bundle, which means that it's a vector bundle of rank 1, then we have that psi k of X is equal to X to the k. Furthermore, we have that it doesn't matter what order you do them in, so you could do psi k followed by psi l, and that's the same thing as psi l followed by psi k. And indeed, actually, it turns out that this is equal to psi l times k, but we don't need that for this video. So just this property here is enough. Furthermore, if p is prime, then we have that psi p of x is equal to x to the power of p mod p. And if x is in the reduced k theory of the 2n sphere, then this psi k acts as multiplication by k to the n. And this is actually a legitimate definition because the first two properties uniquely determine the Adams operations. And again, I think there's an explicit definition in terms of, I think it's exterior powers or something, but these are the properties that we'll need for our proof. So the actual theorem is that if the Hopf invariant is equal to 1, then n is either 2, 4, or 8. N can also be 1, but we'll ignore that case for now. The map, which has Hopf invariant 1, by the way, is the Hopf fibration in these dimensions. And this theorem has some nice consequences, which I won't go into. But I might write a blog post about some of the consequences, because I'm trying to revive the blog, take over all of the whole internet, not just YouTube. The whole internet, all of the different forms of media. I want to take over the blog scene as well, so I might do that. But this has loads of nice consequences. But for us, we just want to prove that if the Hopf invariant is equal to 1, then n is either 2, 4, or 8. That is our theorem of the week. Okay, good. And, okay, so let's write that n is a even number, because the Hopf invariant is necessarily like 0, I believe, when n is odd, so we'll write that n is an even number. Now, what do we note? Well, what does psi do to alpha? Well, psi of alpha, right, I see what happened here. I forgot to put the brackets in. This should be k to the 2m. And why is that? Well, let's look back at what alpha is. Well, alpha is this, so psi, these Adams operations are also natural. So psi k of pi star is the same thing as pi star of psi k. And this generator here is in the reduced k theory of S2n. But what does the Adams operation do to elements of the reduced k theory of the 2n sphere? It just acts as multiplication by k to the n. And so that's where we get k to the 2m times the generator. And because pi star is necessarily a homomorphism, then we can take out this k to the 2m and we're just left with k to the 2m times alpha. So psi k of alpha is equal to k to the 2m times alpha. Now, psi k of beta is a little bit more complicated, but it's not too bad. Psi k of beta is equal to psi k of I star of beta, which is precisely psi k of the generator by definition. Again, because this generator is in the reduced k theory of the n sphere, then this just acts as multiplication by m. But also, on the other hand, we know that k to the m times the generator of n is equal to I star of k to the m times beta, because I star of beta is the generator. And so, what do we have? We have that I star of psi k of beta is equal to I star of k to the m times beta. Therefore, psi k of beta minus k to the m times beta is in the kernel of I star, but because this sequence here is exact, so anybody in the kernel of I star is also in the image of pi star, and the image of pi star is generated by alpha, because the reason for this is because alpha is equal to pi star of the generator, so alpha is going to generate the image. And therefore, we have that psi k. So anybody in the image of alpha is going to be of the form mu k times alpha, where mu k is just an integer. And so if we add k to the m times beta on both sides, then we have that psi k of beta is equal to k to the m times beta plus mu k times alpha for some integer, mu k. Okay, these are the bits of information that we need. In fact, we didn't even need this bit of information. We need this bit of information here. Now we're going to use all of the properties that we need in order to show the theorem once and for all. Okay, firstly, remember that psi 2 of beta is equal to beta squared mod 2, because 2 is a prime number. But psi 2 of beta is also equal to 2 to the m beta plus mu 2 alpha. Now, because 2 to the m is even, this is equal to mu 2 times alpha. But this is also equal to, by definition of the Hopf invariant, if we remember from the start, this is also equal to h of f times alpha. And this is all mod 2. And so if h of f is equal to 1, then we also need that mu 2 is odd. Okay, good. So, now what we're going to do is we're going to use number theory to show that mu 2 is only odd when m is equal to 1, 2, or 4. So, remember that psi 2 composed with psi 3 is equal to psi 3 composed with psi 2. And so we'll just apply it to beta and see what happens. And I'll allow you to check with before, but we get this. And since those two equal, we do some algebra, combine the coefficients of alpha, equate the coefficients of alpha, and this is what we obtain here in the end here. This. Now, what we want is mu 2 to be odd. If mu 2 is odd, then that implies that 2 to the m must divide 3 to the m minus 1. And I'll leave it as an exercise to you to do some number theory. But this implies that m is equal to 1, 2, or 4 as required. And so mu 2 is only odd when m is equal to 1, 2, or 4. When m is equal to 1, 2, or 4, n is equal to 2, 4, or 8. And so we have our result as required. And that is a proof of the Hopf invariant 1 theorem. Admittedly, I haven't given many of the prerequisites since this is just a theorem of the week. This isn't a full-on talk about K-theory. But yeah, that gives you the idea of the proof, at least. You construct these Adams operations, and you effectively use their properties to reduce it to an elementary number theory lemma. So yeah, that's the proof of the Hopf invariant 1 theorem. And yeah, I've got lots of new material coming shortly, so keep an eye out for that stuff. And yeah, I'll see you guys next time. Good day.